It's been nearly 50 years since Atari released their breakout arcade game. This was one of their last games designed in full discrete logic. No microprocessor, no code. In this project, we'll learn this unique circuitry by building our own full discrete retro version. Hi, I'm Paul, and like most people, I love a good bag of chips. I started working on IBM mainframes in the early 80s. Installs, upgrades, features. This is me in a 3033 Model U, my personal favorite. Delicious. This was IBM's last mainframe series designed in full discrete logic. This was before the advent of TCMs like this one, introduced in the 3081. In the mid-80s, I started a company to design and manufacture memory upgrades for IBM 3080, 3090, and 9121 series machines. These upgrades went into government, industry, finance, education, you name it. For example, 144 of these cards would go into a 3090 600E to bring expanded storage to a whopping 2 gigabytes. We used a lot of DRAM, but we also used plenty of discrete logic, mostly fast TTL and 10K ECL. One of my favorite chips is the 10192 quad current mode bus driver. These are like the first half of an ECL gate, just a differential pair without the emitter followers. We use these to drive the data and control buses on 3080 series products. Another one of my favorites is the 7474 dual D-type flip-flop, or the rough ECL equivalent, the 10131. You can use these as a data register, set-reset latch, divider, or any combination you can dream of. Very versatile. Breakout uses 12 7474s, so we're going to have some fun. So yes, I do love a good chip. I'm sure you've got your favorites. Let us know which ones and why in the comments below. That was about as fancy as I get, so don't be too disappointed with the rest, especially this next section, because as usual, we need to take care of a little business first. Now, we already said this is going to be a full discrete version, not a software simulation or an FPGA. We want to try and maintain as much of the essence of the original as possible, but with the luxury of using modern tools. Now, all the heavy lifting was done for us, so this should be fairly straightforward. I'm not going to say easy because we have zero karma at this point, and we're going to need all the help we can get. Now, a full discrete version will naturally have dual player mode and cocktail support, and I'd also love to see full connector support, so if you have a compatible arcade cabinet, you should be able to plug this in and have it work. And then for those of us that don't have an arcade cabinet, let's build a little control board so we can easily drive the thing. Now, let's retro the logic, but I have no personal desire to retro the linear space heater, so we'll probably just use an off-board switching brick. Now, Breakout puts out black and white monochrome video, so let's throw an RCA connector on board and another one for audio so we can easily hook it to a monitor. And the original has no indicators, so let's throw some bling on there and also add some scope probe headers for interesting signals. I looked at the video chain and we're running half speed we need for VGA, so we'll have to see if we can add an option later. First thing we need to do is take a look at the resources out there. We have the manual with schematics, circuit descriptions, parts layout, parts list. There's also a lot of pictures of boards out there. I picked up a couple of crispy ones too for reference. And from that, let's figure out what we need to design that little control board and do that first so we can use it for both breadboarding and production. And then the whole idea is to learn the circuitry, so let's break it into sections and breadboard the whole thing. And as we're doing that, we'll capture schematics. When we're all done, we'll lay out a board, and then we can build and play. We'll drop everything in a repository, most likely GitHub, but I'll leave a link below. This will include any of the source materials that we used in the project. And this is the Eagle Shop, so we'll throw the project files out there, and we'll do a custom library so there's no external dependencies. And naturally, we'll throw a set of Gerbers out there so you can chuck them at your favorite fab. And I'm not sure if we're going to do boards or kits for this one. We'll have to see. One more short waylay before we get started. Now, this is not comprehensive in any way. I just want to do a quick drive-by of some interesting points. There are some great histories of Atari and Breakout out there, and I encourage you to go surfing. And please feel free to correct or add to this, especially if you have any insider knowledge. We'd all love to hear some of that. Atari was started by Nolan Bushnell and Ted Dabney in '71. Back then, it was actually a partnership called Syzygy, and their first task was to engineer computer space, arguably the world's first commercially viable video arcade game, Girl not included. Both of these gentlemen had worked for Ampex, which at that time was the world leader in videotape technology and equipment. Atari was officially incorporated in July of '72, and their first engineering employee was Alan Alcorn, who came from Ampex. Nolan gave Alan his first task of creating a Pong-type game for a customer order, emphasizing that low chip count and quick delivery were paramount. The customer and order were BS.
It wasn't lies, it was just bullshit.
Nolan just wanted to give Alan a task to get him up to speed on video counters and related circuitry. Alan then proceeded to create the very successful Atari Pong game. In '73, Dabney left, and since Nolan is the true driving force here, we'll shift this around a bit. In January of '74, a scraggly 19-year-old kid walked into Atari and told the receptionist he wouldn't leave without a job. Alan took a look and hired the kid to do miscellaneous technical work, repairs, engineering changes, etc. So Stephen Jobs became Atari's 40th employee. Just 3 months later, Jobs went on sabbatical to India for 7 months, then spent 12 weeks at a commune in Oregon before getting his old Atari job back in the winter of '75. In January of '75, Nolan and Steve Bristow, who also came from, you guessed it, Ampex, came up with the concept for a single-player paddle game where the player worked to break through a wall of bricks. Nolan tried to recruit his design engineers to work on this concept, but most thought paddle-type games were passé, and no one really wanted to work on it. Nolan knew Steve Jobs was not a design engineer, but he knew Jobs had a very sharp friend over at Hewlett-Packard. Steve Wozniak would come into Atari at night, play games, and have technical conversations with other engineers. Nolan offered Steve Jobs the task of prototyping this brick game concept, knowing full well that he would get help from Wozniak. Nolan offered a flat fee of $700 for the prototype work, plus a $1,000 bonus for every chip under 50. I'm not really sure why the $700 fee if Jobs was already an employee, but I do kind of understand the extra per chip bonus because chip counts were getting out of hand. For reference, Pong used 76 chips and many other Atari products used in excess of 100. Now, Nolan never actually gave a deadline for the work, but Steve Jobs, being antsy to head back to Oregon, told Wozniak they needed to finish it by the weekend. So Wozniak went to work at HP during the day and designed this game at night, while Jobs did the physical wire wrapping. A working prototype was delivered in 4 days with just 45 chips, earning a $5,000 bonus. As an extra special bonus, they both got mono. Jobs was paid and gave Wozniak half the $700 fee. He had never told Wozniak about the per-chip bonus and kept the entire $5,000. Now, Wozniak loved this type of work and would have done it for free, but this slight omission would put a dent in their relationship later on when it came to light. This prototype work would have been done between winter and spring of '75, sometime between the concept shown in corporate records in January and Wozniak's mention of a brick-type game in the Homebrew Computer Club magazine in April. There are some records of the prototype bouncing around within engineering at Atari during '75, but the final work to make a production version was done by Gary Waters of Atari's Cyan Engineering Division in late '75 or early '76. The final Rev A production version had a whopping 102 chips. But a lot needed to be done to make the prototype into a reproducible, marketable game. This included adding sound, on-screen scoring, dual player support, cocktail mode, coin mechanism logic, and to beef up unstable video chain shortcuts used by Wozniak to reduce the chip count. When we're all finished with this, a good exercise would be to see how low we can go by removing stuff to get as close to the original prototype count as we can. In '76, Jobs left Atari to start Apple, and Breakout was introduced to the public in June, selling over 14,000 cabinets during its lifespan. Any criticisms I may have of the circuitry later are completely mooted by the fact that they sold a shitload of these. Finally, let's get into it. We'll drop everything in GitHub under ByteMineDev, Breakout, and I'll start with the legacy folder, and the first thing we'll drop is this document. Feel free to stop and grab it. As you can see, this is the fourth printing of the Operation, Maintenance, and Service Manual. Page 2 has a table of contents. The whole theory of operation section is really nice, especially the circuit descriptions. And what we're really after here, the schematics. Page 6 has this block diagram. You can see the game has simple controls, just start and serve buttons and the paddle potentiometer. Page 9 has circuit descriptions. These are pretty good, and we'll revisit some of these later on. The monitor is monochrome, so to get color, they added colored strips directly to the monitor surface. Page 34 has wiring harness. This shows the PCB connections to power, speakers, buttons. You can see how the paddle, player start and serve switches are wired up, and also the coin mechanisms, and connections for a cocktail table. The 44-pin edge connector is labeled 1 through 22 on the solder side, starting near the regulator, and A through Z on the component side, skipping letters G, O, I, and Q, so they're not confused with zeros and ones. Schematics start on page 35 and are broken up into 2 pages per sheet, which is kind of sucking for viewing, so the first thing we'll do is stitch these together into single sheets. So sheet 1 has a revision list, and as you can see, this is done in ANSI size D, which is 22 by 34. And you can see the schematic is for revision F boards. Page 43 and 44 have parts lists. You can see the standard 7400 series TTL, this bipolar RAM, but it also has some 9000 series TTL. Page 45 has board layout. Kind of crappy, but better than nothing. We'll probably roll our own for clarity. And lastly, on page 46, they were kind enough to include the schematic for the Motorola monitor. Now, I purposely opened this with Acrobat because it has this great export as image function. The only options you have is to pick the image format and destination folder. And yes, I should have used a lossless format, but I already had a lot invested in cleanup, so you're stuck with JPEG. You can't select which pages to export, so we just need to let it do its thing, and we'll cull what we don't want. If you look at the details, you'll see that the images are quite high res. Let's let this finish and take a look. Schematics start on page 35. Pretty good, I think. Let's cull what we don't need. We also don't need images of the parts list, so we'll get rid of those, and we'll rename these to something more palatable. Oops, fix that. Don't laugh, but I'm going to combine these using MS Paint. I'll start with a new image, double the exported size. Copy in the first half directly, then crop and copy the second half in a line. Let's crop the whole thing, clean it up a bit. Save it as just the single sheet and do that for the rest. Let's kill off the half files and drop these 4 images into GitHub. One great thing you'll find is that many of your local office supply stores can print these. Let's upload the staples and get some prints. The originals are size D, basically 2 by 3 feet, which would be fun to have, but I think I'll just print a set in size C, which is more manageable, basically 18 by 24. And we should get those in a few days. So while we're waiting for those prints, let's take a quick overview of the schematic images, and we'll cover more details when we're breadboarding. So on sheet 1, we've got the oscillator and clock generator. We've got the video counters. We have boundary generation, so this is basically the white line around the edge of the screen. We've got the video sync counter, summing, and composite output. We've got the ball position counters and ball movement logic. We've got the ball counter and serve logic. And finally, we have brick storage, display, and hit logic. Now, if you remember, Gary Waters took the prototype to production, and in an interview with Atari historian Martin Goldberg, Gary revealed a few interesting things. First, the prototype drawing he received was done on a single C-size sheet, and he had it in his design files until he was let go in '84. I know we've all lost stuff, but this is a tough one. Now, I believe much of what was on that sheet ended up on sheet 1 here, because you have everything for a minimalist game except for the paddle logic. Now, Gary also said the prototype was a single player and had no sound. Everyone agrees on that. He also said it had no scorekeeping. And this conflicts with what Wozniak said. In at least one interview, he said that he argued with Steve Jobs about whether the score should be on the top or the bottom of the screen. And someone else mentioned that the score was off-board on an LED display, so we just don't know. Another thing Gary mentioned was issues with the video counters and sync circuitry. Now, I don't know what it was, but it could have been something like a self-referencing gate where you use that same short pulse to drive something else, like a reset or a load circuit. And that would completely depend on that particular chip's input characteristics, so it would be very unreliable. Now, in the original, at least on this circuit here, the original ball motion logic would have been in this area here. And you can see other circuitry was added to make it more fancy, or to support the flip screen in cocktail mode, and also to speed up the ball's motion after a certain number of volleys. So that would have been some circuitry here. In the ball counter and serve logic, you can see some 2-player support over here. And you also, I'm not sure if the ball counter was actually in the prototype or not, but there would have been plenty of room here for the paddle logic. But in the production version, that paddle logic was moved to sheet 2. Okay, on the second sheet, we've got the brick score logic. So basically for each layer of bricks, there can be a different number of points attributed to that layer. So this determines that. Then we've got the actual score counters themselves. We got what they call empty wall detect. So in the game, you can have 2 walls of bricks. You can eat through 2 walls of bricks. So this circuitry detects when the first wall is done and puts up a second wall. We've got the actual digital display for both the scores and the ball counters. And then we've got that paddle logic we talked about. And then finally up here, some sound and logic and amplifier. For sheet 3, we've got the reset logic. We've got coin logic. Then there's the coin counter, start game logic, and bonus logic or free game selector. On the final page, we have the screen flip logic, and this is for player 2 in a cocktail mode. We've got these pull-ups, and finally we've got the power supply. A couple of interesting things. We see the drawing was started sometime mid-December of '75. The other sheets have the 16th, but it's no big deal. I think the 15th was a Monday. In the revision list, we can see the production release was done 2 months later, followed up by revision B a month later with 3 engineering changes. Then 3 weeks later, revision C with another 3 engineering changes. 3 weeks later, revision D, 1 engineering change. 1 week later, revision E with 1 engineering change. And 2 months later, the final release that we see a lot of with 2 engineering changes. Now you can see the revision number on the solder side of the board, which is kind of, we've got a lot of pictures of the fronts of boards, so we really don't know from the picture what the revision is. We can infer from the fixes that are on it, but we really don't know. So, and then they really didn't make too many of these. We see an A at serial number 005. You can see on the front they have a serial number stamp. I've got this Rev C board at 019. 2 boards, a 512 and an 824. Don't know what the revision is. We have a revision E at 3677 serial. We have then a revision F at 10537 and another revision F at 16,000 something. So they really didn't make too many of the first ones. They just really quickly got this thing in production ready. Now, if you look on the bottom here, you'll see that the drawer changed the font. Well, changed the word, not the font. You can see it was probably whited out and replaced. What we can see is that on revision A, the board was originally called Breakthrough, and that aligns perfectly with Wozniak's article about a breakthrough game. And on the version C, at least, we see it's Breakout. Now, they've got the exact same part number. And no clue, probably they at least C and above it was called Breakout, and A it was called Breakthrough. So it never got to a customer as Breakthrough. Another really interesting thing is the use of De Morgan notation. For example, here we've got this NOR gate, the 7402, which is quad NOR gate, and we've got another gate in the exact same package down here, but it's shown as a negative input AND. So these two are actually logically equivalent. And you'll see more of this stuff around, like we've got this negative input OR gate here, and the 7400 is clearly a quad NAND gate. We see a 7432 gate here, which is a quad OR, and so this is a negative input NOR. And so you'll see a few of these things around here. So here we've got our normal positive logic where, as you know, for an OR gate, either A or B is high, then the output is on. And for an AND gate, both A and B must be on in order for the output to be on, and NOR and NAND are simply the same thing with flipped output. Now for De Morgan notation, they're saying that this OR gate is the same thing as this negative AND gate. So if you think about the logic, if A and B are low, then the output is low, so that makes perfect sense. And then for the negative input NOR gate, either A or B has to be low, then the output will be low. And then the other gates follow the same pattern. So it is pretty easy to see that in this case, they want both both of these inputs to be low in order for the output to turn on. Now, I'm not sure who is the De Morgan Logic person. I went looking on the interweb for hand-drawn stuff from Wozniak or any logic drawing attributed to Wozniak. I actually don't find any unless I have a serious case of the dumbass. I can't find any hand-drawn or sheets with his name on it. But if you look back at some of the other Atari things, you look back at the original Pong, it's got De Morgan notation. So I'm not sure if it's an Atari thing and it's just a standard they set. Another interesting thing is the drawing was probably originally made without cocktail support, simply because of the notation, the prime notation on the video signals, and also a little bit of alignment. So if you would just take this 128 Victor line down, fits right there. This is probably how the original was drawn. And then they took the original lines, added the prime, brought all those signals over to page 4. This is the last thing that was added. Put the primes into this circuitry here and get out the regular signals that's used in the logic. Let's take a quick overview of the board as well, and we'll start with the power supply. In the upper right, we have this LM323 regulator. This is like a 7805 in a TO3 package, but 5 volts at 3 amps. We have these input rectifiers. No, we don't need a bridge because they're using a center tap transformer where the center tap is hooked to ground. 8000 mic electrolytic over here on the input to the reg and a 220 mic on the output. Interesting that they only have 7.1 mic decoupling caps, where today we put them near every device. One thing I can't wrap my head around is the 4 ohm resistor between the regulator input and output. I'm not sure if this is a load to prevent startup spikes or shutdown spikes. I can imagine the reg fighting like hell to keep the output at 5 volts. Or perhaps it makes it work less. Someone let me know. You do see a lot of crispy boards out there, so these parts are pushed to extremes. If we were going to refurbish any of these old boards, I would definitely replace the regs with these switching drop-in replacements. You wouldn't even need a heatsink. Next, we've got some configuration switches. This one is for the number of plays per coin. This one is for 3 or 5 balls per play. And this one here is for cocktail versus upright mode. I don't remember which way these go, but you can look it up in the manual. These smaller dip switches, we'll get to it in a bit. You can see the chips are in a 12 by 9 matrix labeled A through N on the short side and 1 through 9 on the long side. They skip letters G and I like we saw before. I initially thought they skipped G because it was kind of like in the middle of the board, but I think it's a nomenclature convention to avoid confusion with zeros and ones. I'm going to keep the board in this orientation even though the chips are upside down because it feels more natural to have Able 1 in this corner and Nancy 9 over here. I also like to have the main logical flow from left to right. Plus it fits the widescreen better. So we'll refer to the chip sites as Able 1, Baker 1, Charlie 1, Dog 1, etc. instead of the modern Alpha Bravo Charlie Delta, because that's what IBM used and it's pretty much seared into my brain. IBM is pretty old and Able Baker Charlie Dog was a phonetic alphabet used in World War I. IBM also skips letters O and I, but they don't skip G or Q. The guy that laid out this board was an Atari contractor, Howard Canton. You can see his work in other Atari products, as well as the Apple II. Definitely an artist. Way more Rembrandt than Picasso. The board is harder to break up into clean sections because of shared gates, so this is going to be pretty rough. So here goes. We've got the clock and divider. We've got those horizontal and vertical sync counters. Got screen flip logic for cocktail mode. We've got that brick storage bipolar RAM. got the score counters, the digital display, including this 555 player up flash timer. We've got ball motion counters, the ball motion logic, got the ball in play counter, paddle logic, paddle size, points per brick layer counter, and a logic to reset the wall when the first one's cleared. We got coin stuff, got the coin counter, we got free game logic controlled by the dip switches, we got the start game logic, and we got some sound one-shots and the amplifier. So after reviewing the schematics, boards, parts list, it looks like we have some chip challenges. As we go down the parts list, you'll see mostly common 7400 series TTL, plus a couple of 555s, a 4016, and the LM380 audio amp. But there's also some older National 9000 series chips. There's this 7483 adder we'll talk about later, and also this 256x1 bipolar RAM. In fact, if you add up the types in the parts list, there are 98 TTL, 3 linear, and 1 CMOS chips. That's 102. But if you look at an actual board, there's 103. So going over the F schematics, I noticed there are no Charlie 1 gates on the drawings, but there's clearly a chip in Charlie 1 on the board. There are also more resistors, capacitors, and diodes on the board than on the schematic. So I think our next task will be to compare the Rev F board and schematic and update the schematic properly. And naturally, we're going to believe the board because they work. So let's narrow this down a little. The 7400 series is easy. We can simply use commonly available low-power Schottky parts, which have similar drive fan-out, propagation delay, and input sensitivity, but on average use about half the power. The 555s, the 4016, and LM380 are all still manufactured, so that's easy as well. Now, if we look at the other chips in question, you can see that they're no longer manufactured. You can sometimes find them on eBay, but at a premium, and we want to be able to afford to build this. One chip I rarely find on eBay is the 9312 MUX, but I digress, so let's discuss these in sequence. First of all, the 9310s and 9316s have 7400 series pin-compatible replacements, and I often see the 7400 series parts on later breakout PCBs, so these are no-brainers. For the 9312s, we can use 74158s, but while functionally equivalent, they're not pin-compatible. This means our PCB won't be the exact pinout of the original, but the logic will remain the same. Now we can put two footprints next to each other on the board, but if we can't get the parts, I don't see any benefit considering the added complexity. Now let me know your thoughts about this. My feeling is we just use the 158s. For the 9602s, we can use 123s. Once again, not pin compatible and also not 100% functionally equivalent. First of all, the timing is slightly different, but I don't think the difference is material. These are mostly used to time the duration of sound effects, and you wouldn't notice the difference. There are some slight logic differences, however, that we need to discuss. First of all, the 9602s have an OR trigger input, while the 123s use an AND. Now, this is not too big of a deal, right? All instances use only one of the inputs and tie the other. We just need to make sure we tie the other input to the correct level. The problem here is that the 9602 has a synchronous reset, but the 123 reset also ties into the trigger. So if the conditions are right, releasing the reset line can trigger the one-shot. We'll have to see if this condition exists in any of the instances and figure out how to suppress spurious retriggering if necessary. No idea. I listed the 7483 here because I'd prefer to use 283s instead for a few reasons. First of all, I haven't found anyone still making this part. It also has a strange printout with the power pins in the center of the package, typically for extended temperature or military applications. I'm not sure why they did the 7483 like this, but they normalized it in the 283, which we can get. Now they're still a bit pricey. These two adders are used in the vertical video chain to shift the image slightly on cocktail modes when player 2 is up. So if you're not going to be using two-player cocktail mode, then we should provide some onboard jumpers or something that allows us to bypass the flip logic and not have to populate these adders. As long as the reduced delay doesn't mess anything up. You never know. So the last challenge on this list is the bipolar RAM, which is used for brick storage. Not made anymore, but nothing we can do but buy them off the interweb. And fortunately, a lot of companies made these compatible parts, so I'll drop a list in the docs. You can also use open collector versions of these chips. For example, we could use the 82S17 with a pull-up resistor on data out. And you see many boards with pull-up resistors soldered from data out to VCC, so I'm assuming these are all open collector versions.
I think we've had enough fun for now. In the next part, we'll trace out the RevF board and update the schematics.